A robot that only navigates stops at the doorway of usefulness. The hard problem begins when it must touch the world, pick apart, open a drawer, fold fabric, or assist in surgery. Manipulation is where abstract intelligence meets friction, mass, and contact. Grasping is the gateway skill. Without reliable grasps, even the best vision stack and language model cannot unload a truck, assemble a phone, or set a table. Warehouse throughput, surgical precision, and home assistance all converge on dependable contact. Manipulation combines perception errors, imperfect models, and irreversible contact events. A slight misalignment turns a stable grasp into a dropped package. Soft objects deform. Transparent and reflective items fool depth sensors. Clutter hides collision geometry until the hand is already moving. Unlike text generation, there is no undo button when a glass shatters. Every successful grasp is a small negotiation between what the robot believes and what physics allows. Partial observability means the robot commits to grasps before it sees the full object shape. Grasp planning starts with geometry. Where can fingers or a suction cup touch without collision? Physics decides whether those contacts can resist gravity and disturbance. Friction cones, center of mass, and wrench feasibility determine if a grasp is stable or a slip waiting to happen. Simulation helps explore candidates, but real materials vary. A polished metal part behaves differently from a cardboard box with crushed corners. Analytic grasp wrenches summarize whether contact forces can resist expected disturbances. Forward kinematics computes where the hand sits given joint angles. Inverse kinematics asks which joint configuration reaches a desired pose. Redundant arms have infinite solutions, so planners pick smooth, energy-efficient postures that stay away from singularities. Mobile manipulators add base motion to the same problem. A grasp is useless if the arm cannot reach it without hitting shelves, the robot body, or a nearby human. Null space motion lets redundant arms avoid joints limits while tracking the same hand pose. Dynamics reasons about forces, torques, and acceleration. Picking a heavy battery pack stresses shoulder joints. Fast motions excite vibration. Compliant contacts absorb impact instead of bouncing objects away. Force torque sensors at the wrist reveal when a grasp is slipping or when a peg is aligned in a hole. Control loops running at hundreds of hertz translate these signals into micro-adjustments humans never notice, but robots depend on. Impact forces during fast picks can exceed static load ratings unless trajectories limit acceleration. Grasp planners generate many candidate hand poses around an object, score them for stability and reachability, and filter collisions. Analytic models use shape primitives. Data-driven models learn from thousands of simulated grasps. Once a grasp is chosen, approach trajectories matter. Come from the right direction, pre-shape the hand, close fingers with controlled force, and lift slowly until weight is confirmed. Rushing any step increases drops. Suction cups add seal quality uncertainty that geometry-only planners easily overlook. Affordances describe how an object invites interaction. A mug handle affords a precision grip. A flat box top affords suction. A handle affords pulling. Vision models increasingly predict grasp affordances directly from images, skipping explicit three-dimensional reconstruction when time is tight. Affordance reasoning connects perception to action. The robot sees not only a mug, but where a successful grasp is likely, even among clutter. Cluttered bins demand ranking many affordances per object, not a single canonical grasp. Parallel grippers dominate warehouses because they are simple and fast. Dexterous hands with 4 or 5 fingers reorient objects in hand, tool use, and delicate placement. More joints mean richer manipulation, but harder control and calibration. Tendon-driven hands compress hardware but complicate modeling. Research humanoids push dexterity for general tasks. Industry often chooses the simplest gripper that meets reliability targets and cycle time. In-hand manipulation reduces regrasping, but increases control bandwidth and calibration burden. Humans routinely use 2 hands, one holds, one operates. Bimanual robots stabilize large sheets, peel packaging, and assemble parts that exceed single-arm reach. Coordination requires shared task models, collision avoidance between arms, and timing so both contacts remain stable. Handoffs transfer objects midair or on a fixture. Dual-arm cells appear in electronics assembly and humanoid research, where general manipulation is the goal. Shared workspace planning must prevent arms from fighting over the same volume mid-task. Vision alone cannot detect incipient slip inside a closed gripper. Tactile skins, force arrays, and fingertip sensors measure pressure distribution and vibration. Slip triggers immediate force increases or finger repositioning. Texture sensing helps distinguish materials. In insertion tasks, compliance felt through the wrist beats vision blocked by the workpiece. Touch turns manipulation from open-loop motion into contact-aware control. High-resolution tactile arrays enable localization of contacts smaller than vision resolution. Position control tracks trajectories when contacts are predictable. Force control pushes with constant effort for wiping or polishing. Impedance control behaves like a virtual spring damper, yielding on contact instead of fighting it. Hybrid schemes switch modes during a single task. Free space approach in position, compliant insertion in impedance, firm hold in force. Getting these transitions wrong creates chatter, bounce, or crushed objects. Admittance control lets the environment guide insertion instead of forcing rigid trajectories. Learning accelerates manipulation when analytic models fall short. Teleoperation collects human demonstrations for imitation learning. Simulation generates millions of grasps across object sets. Policies trained in sim require careful transfer to real hardware. Foundation models for robotics aim to generalize across objects and instructions, but deployment still demands safety limits, fallbacks, and verification on the exact cell where the robot works. Real-world fine-tuning still requires guardrails because learned policies can exploit sim quirks. Tesla Optimus and Figure AI target general-purpose manipulation in factories and homes. Amazon Robotics scales picking and fulfillment with specialized end effectors and dense sensing. Surgical robots translate surgeon intent into sub-millimeter motion with haptic feedback. Each sector optimizes different metrics: cycle time in logistics, sterility in surgery, versatility in humanoids. The through line is the same: reliable contact with the physical world at scale. Return on investment often hinges on mean time between drops, not demo grasp highlight reels. A production manipulation stack chains perception, grasp planning, motion planning, control, and verification. Vision segments objects and estimates pose. Grasp planning proposes contacts. Motion planning finds collision-free approach and retreat paths. Control executes with force limits. Verification checks weight, vision, or tactile cues before releasing to the next station. Failure at any stage should trigger recoveries, rescan, regrasp, or ask for help. Human-in-the-loop stations remain essential when SKU variety exceeds model coverage. Manipulation metrics must reflect deployment reality, not lab averages. Report success under clutter, lighting change, object variation, and cycle time pressure. Track near misses, slips caught by tactile sensing versus drops on the floor. Log which failure mode dominated. A 99% bench result can collapse in production when SKUs change weekly. Continuous evaluation drives gripper choice, sensor placement, and when to escalate to human pickers. Shift-level statistics reveal drift when lighting, wear, or supplier cartons change silently. Robot manipulation turns perception into physical change. Kinematics and dynamics connect joint motion to stable contact. Grasp planning and affordances decide where to touch. Dexterous and bimanual systems expand what is reachable. Tactile sensing and control loops handle uncertainty at contact. Learning and industry deployments push reliability in warehouses, factories, and operating rooms. Master grasping and a robot stops observing the world from a distance, it begins to reshape it. Reliable manipulation is earned through contact-aware sensing, conservative control, and honest metrics.